Now let us continue with 5.1g. Explain the ideal and non-ideal behaviors of gases in terms of intermolecular forces and molecular volume. Okay. Now, what is the difference between ideal gas and real gas? Ideal gas behave ideally at low pressure, high temperature. They obey all the gas laws and ideal gas equation. Okay, real gas is at high pressure, low temperature. They do not obey gas law and ideal equation, but instead they follow van der Waals equations. Okay, so the conditions for ideal gas is low pressure, high temperature because at low pressure, the gas molecules are very far apart, so the negligible intermolecular force of attraction. Okay. At high temperature, the gas molecules are moving very fast, further away from each other. Thus, the intermolecular force of attraction is also negligible. Okay, now we explain the conditions at which real gas approach the ideal behavior. Okay, so real gas is at high pressure, low temperature. Real gas is non-ideal gas because the characteristic is the molecules occupy space and have volume. Molecule experience intermolecular forces and they fail to obey the ideal gas equation and gas law, but they obey van der Waals equation better. Okay, so this is the graph. Ideally, it should be constant 1. Okay, but if you can see for other gases, okay, for example, methane, ammonia, even hydrogen gas, it deviates from the ideal gas in terms of calculation. So why real gas deviates from ideal behavior at high pressure? So we can look at this. This is low pressure. This is high pressure. At high pressure, the molecules are closer and the space occupied by molecules becomes significant. Thus, the intermolecular forces is significant. Okay. For real gas, the volume of gas no longer is the same as volume of container. Just a reminder, when pressure increases, the distance between the molecules decrease. Thus, the attractive forces develop because when they are close enough, there will be attractive forces. Now, let's look at the explanation here. At low pressure, there are relatively few attractive intermolecular interactions to lessen the impact of the molecule striking the wall of the container, and the pressure is close to that predicted by the ideal gas law. Right? For example, PV equals to nRT. Now, because the attractive is force intermoleculars is fewer, so this molecule can hit the wall frequently because it is not attracted by other molecules. Okay, however, at high pressure, the average intermolecular distance relatively small. So the effect of the intermolecular interactions is to lessen the impact of a given molecule striking the container wall, resulting a lower pressure than predicted by ideal gas. For example, maybe it can hit 3 times if let's say it is at low pressure, but because it is high pressure, other molecules are close to it, thus there are intermolecular forces which cannot be ignored. So it maybe can hit the wall only twice. That's why we say that it becomes lower pressure than predicted. Okay. Another one is real gas deviates from ideal behavior at low temperature. Okay, why? At low temperature, the kinetic energy of the gas molecule decreases. So molecules move slower and it becomes, again, same thing, when it is slower, it becomes closer. When it's closer, the intermolecular attractive force is significant. Thus means that, okay, initially if it moves fast enough, it can maybe hit the wall 3 times, for example. But now because at low temperature, the kinetic energy decrease, all the molecule move slower and becomes closer. So when it becomes closer, the intermolecular attractive force is significant. Thus, the measured pressure of the real gas is less than expected. So deviation from ideality is bigger at low temperature. Okay, now we can look at the graph again. So PV per RT is supposed to be equals to 1. Okay. However, only when temperature increase, the gas more closely approaches to ideal behavior. So in general, deviation from ideal behavior increase as temperature decrease. Now we go to van der Waals equation. Okay, real gases do not follow the ideal gas as intermolecular force of attraction cause the measured pressure of a real gas to be less than expected. So when the molecules are close together, the volume of the molecules themselves becomes a significant fraction of the total volume of a gas. Thus, the ideal gas equation is modified to correct the volume of the molecules and for the intermolecular attraction and pressure. So this gives rise to van der Waals equation. Okay, correction for volume. Supposingly the volume of gas is equals to volume of container because the gas can travel everywhere because they are not attracted by the intermolecular forces. Okay, for real gas, however, molecular volume is significant. The volume of gas no longer equals to the volume of container. For example, these two molecules, they are attracted to each other. So if the other gas want to move, they can only move at this space only. For this part, it can no longer move inside because it is already occupied by the molecule. So we use the correction NB. Now, for van der Waals equation, just now as we said, the real gas pressure is less than the ideal gas equation. Therefore, we add in N2A over V squared is added to, for example, PV equals to nRT. Now, the real gas, the P has decreased. Thus, we need to add correction. Okay, so A is constant relates to the strength of intermolecular attraction between molecules. The larger the A, the bigger the molecular size, the stronger the attraction. Another one is correction due to the molecular volume. The volume available is less, thus must be subtracted from the total volume occupied. So B is constant relates to particle volume. The larger the B, the larger the volume. Okay, so each gas has a different value of A and B. So the greater the A means the stronger the attraction. Same thing with B. The greater the B, the greater the molecular volume. Now we can have a look at this. Okay, if it's ideal gas equation, it is low pressure, high temperature. The gas molecules will move very fast, okay, and then you can see it is not attracted to anyone. However, if we look at another one, okay, for example, if we look at this, if it's at low temperature, it moves very slow, so it will be attracted by the others as well. Okay. High pressure is because you can see that the volume here is becoming smaller, so we have high pressure. Okay, now let's look at this van der Waals equation. Okay, so the van der Waals equation, the volume that this molecule can travel is only up here. Okay, because this part has been occupied by the gas. Okay, so this is what we call the molecular volume. So the volume that the gas can travel is minus NB for the correction. As for this part, for the pressure, okay, maybe initially it can only hit, it can hit twice or three times, four times, five times. But when it comes here, there will be attraction, intermolecular interaction between both molecules. So it will move slower. So instead of maybe three, four times, maybe it can only hit two times. Thus, we need to have the correction for pressure because pressure is lower than expected. Okay, another one, as we can see here, if it's smaller, the molecule is smaller, it has bigger space. If the molecule is bigger, then it will have smaller space to move about. So the deviation from ideal gas equation is even larger. So as conclusion, go back to the van der Waals equation. Okay, the pressure will be of real gas is less than ideal gas. Okay, then the volume is the same, the volume is also less. That's all for van der Waals equation, ideal gas versus real gas.